is use Gauss's law to find an expression for the electric field inside the cylinder. Let's start by writing down Gauss's law. So Gauss's law says that the net electric flux is equal to the electric field dotted with the area of a Gaussian surface, and we take the integral over that closed surface, equals the net charge within the Gaussian surface divided by the constant epsilon naught. So if we're talking about a Gaussian surface, first thing we should do is identify our Gaussian surface. Here's our cylinder of charge. We want the electric field inside, so we should pick a Gaussian surface inside. To use the symmetry, we should have the same symmetry, so let's pick a cylinder that's inside. So here's our Gaussian surface. It's a cylinder with radius less than the radius of the cylinder. So we don't get too confused with all these r's. Yeah, we can call this guy little r. So this radius is little r. Gaussian surface, radius r, less than the radius of the whole cylinder. So that's our Gaussian surface. So the two things we want to sort out, what do we write down for the integral, what do we write down for Q inside? Let's do the integral part first. So the integral of E dot dA is the integral of E times dA times cosine theta. In our cylindrical symmetry, the electric field comes off in all directions. The area of our Gaussian surface, the cylinder, points straight out from the surface of the cylinder. So the electric field and the area vectors are parallel. So that leaves us with the integral of E times dA. If we're a constant distance away from the center, we have a constant electric field. E comes out front. Integral of dA is just A. That's the area of the cylinder. 2 pi r times the length. I'm going to call the length of our Gaussian cylinder little l. So there's our left-hand side. What about our right-hand side? What is Q in? Well, Q in is the addition of every little bit of charge inside that cylinder, dq, just like we did in the previous part. dq is rho times dv. Let's fill in what we found for our rho in the last part. So that's our coordinate r. Now we're starting to get a little bit confused. For Q in, we want to calculate all of the charge within this Gaussian surface. So when I write down r here, I'm summing up contributions due to little shells within here. I'm trying to build that integral. So this r is not the same as that r. This is one cylinder within here, so I'm going to call that r primed. R primed times 3 lambda over 2 pi r cubed. That's our expression for density. dV is a volume element within here, a thin shell. So like we had before, that thin shell has a volume of 2 pi times r primed times the thickness dr primed, a little bit in that direction, times the length of the cylinder. So inside of our Gaussian surface is a little shell that has a radius r primed. Our Gaussian surface is out here. Our Gaussian surface has radius r, and our total cylinder is out here with radius big R. Okay, there's all our different variables. This r primed goes with one shell, and we're adding up all the shells to get the total charge inside our Gaussian surface that has radius little r. Our big cylinder has radius capital R. Okay, let's simplify this a bit. We've got a 2 on the bottom and top, pi bottom and top. And I think that's all that cancels. Let's take our constants out front. 3 is a constant, lambda is constant, length of the Gaussian surface is constant, and r cubed is constant. Leaves us with the integral of r primed times r primed squared, dr primed. Our limits of our integral are from the center to our Gaussian surface, because we want the charge inside the Gaussian surface. So 0 to little r. 3 lambda L over r cubed, it's out of r primed cubed over 3 evaluated at r and 0. So this is going to give us r cubed over 3 lambda L r cubed times r cubed over 3. We see that those 3's will cancel, and we've got lambda times L times r cubed over r cubed. There's the charge inside our Gaussian surface. Okay, let's put that in here, let's put this in here, and see what we get next. So there's an expression that has our electric field in it now. If we want to solve, we'll bring our 2 pi r L to the other side. We see that those L's will cancel. So we get E equals 1 over 2 pi epsilon naught. Let's just make that clear what we're doing here. 1 over 2 pi epsilon naught times lambda times r squared. We have an r here, r cubed here, so r cubed over r gives us r squared. And then we also have our r cubed on the bottom. So there's the magnitude of the electric field. Electric field, of course, is a vector. The direction is straight outwards, radially outwards. And then this is true for r less than or equal to the radius of the cylinder. For a positive charge, it points out. Negative charge, it points in. So we're going to assume we have positive charge, and it points out everywhere. And the last, so there's our electric field within the cylinder. The last thing we're asked to check is, does our expression have the expected value at the surface, so where little r is equal to the capital R? So for part D, at the surface, means r is equal to the radius of the cylinder. There we have that our electric field is 1 over 2 pi epsilon naught times lambda times r squared over r cubed, which gives us 1 over 2 pi epsilon naught times lambda over r. That's the same expression as any long thin wire, which you can find using Gauss's law. So yes, this does give us the expected result.